Hey there, Keys Pre-Calculus. I hope y'all are having a great snow day, but you're going to have to take a little break to learn about partial fraction decompositions with me. This is something that you're going to be using in calculus, so we're going to introduce it now. We are in Chapter 7, the last half of Section 3. And we're going to work on this today on the video because we cannot meet in class because we're snowed out. So what is partial fraction decomposition? Well, it's when you take a rational expression like the one I have up here in pink and you decompose it into the sum of two or more simpler rational expressions like the green one and the blue one. So the green and the blue are both partial fractions that make up, or that when you're added together and simplify it, it would end up being the pink fraction, which is a little more complicated. How do you decompose the pink fraction? Well, I'm glad you asked. On page 479 in your book, they have a blue box that tells you step by step how to do it. However, I think it's easier just to walk through a problem or two to see how it works, and then I think you'll have no problem understanding how this process works, and I don't think you're going to have any problems doing it. So let's get started. First of all, I'm going to rewrite my pink fraction. Wow, isn't that cool how I did that? And now I want to look at the denominator. X squared minus x minus 6. I want to factor that. So I'm going to factor it into its linear factors, which is x minus 3 and x plus 2. And I'm going to rewrite them up here as denominators. Okay. And x plus 2. But I don't know what my numerator is. My numerator has to be something that adds up to be x plus 7. And since I don't know what it is, I'm going to call my numerator of my first one a and the numerator of the second term b. So now what I'm going to have to do is find a basic equation that equates a plus b to x plus 7. And I have to do that by finding the least common denominator and adding those fractions together. Well, obviously my least common denominator, not necessarily my least, but a common denominator, and in this case the least common denominator is going to be x squared minus x minus 6, but it's going to be the linear factors that make that up. Or rather, it's easier to think of the least common denominator in terms of the linear factors. In other words, I want to rewrite a plus b as a single unit with the denominator of x minus 3 times x plus 2. Okay, so I have to ask myself, what is missing from a? Well, a over x minus 3 is missing the x plus 2. So I would multiply my a times x plus 2, and then I would multiply my b times x minus 3 so that I can combine them into one expression. From here on out, I just want to work with the numerator. So I'm going to write x plus 7, and that's going to be equivalent to the numerator of this expression above. So what I'm going to do now is distribute my a to get ax plus 2a, and then I'm going to distribute my b to get bx minus 3b. And now what I want to do is collect like terms. So I'm going to take my ax here and my bx, and I'm going to write them together. So ax plus bx. And then I'm going to come over here and collect, let's see if I can get this over here, my 2a and my negative 3b, and collect those together. Plus 2a minus 3b. So then I'm going to factor those like terms. So I'm going to say x plus 7 equals, if I factor the ax plus bx, I get a plus b times x, and then if I factor the, well, I'm not going to factor that. There's nothing to factor out on that one. So that's just the same as saying 2a, because those are like our constants, minus 3b. So now I'm going to equate the coefficients of the left side with the coefficients of the right side into a system of equations. So basically, because the coefficient of x on the right side is a plus b, and the coefficient of x on the left side is just an understood 1, I'm going to rewrite over here on the left, because I was running out of room, a plus b, because that's the coefficient of the x value on the right side, is equal to 1, because that's the coefficient of x on the left side of my equation. Next, I'm going to take this 2a minus 3b right here, and I'm going to equate that to the 7, because those are my constants. And I'm going to rewrite it over here in my system. So 2a minus 3b is equivalent to 7. And now I'm going to solve for a and b with either elimination or substitution, whichever way you find easiest you can do. I think in this case I'm going to use elimination. So I'm going to multiply my first row by 2, and I'm going to get 2a plus 2b equals 2. And then I'm just going to subtract down. Whoops, sorry. So 2a minus 2a is nothing. Negative 3b minus 2b is negative 5b. And then 7 minus 2 is 5. Therefore, b equals negative 1. Now I'm going to take that negative 1 and I'm going to substitute it into this top equation. It's orange, but I'm going to use purple just to distinguish it. So I would say a plus, instead of b, I'm going to substitute a negative 1 in place of there, equals 1. And so a equals 2. So now what I can do is I can rewrite this a up here, which I would not ask you to I would ask you to completely rewrite it. But I'm running out of space here. So I'm going to substitute this 2 in place of my a, and I'm going to substitute negative 1 in place of b, and you see that we have decomposed the pink x plus 7 over x squared minus x minus 6. So we decomposed the pink rational expression into two simpler, or the sum of two simpler rational expressions. That's called partial fraction decomposition, where the sum, each term of the sum is a partial fraction of the original. See how simple that is? I'll give you a second just to look over what we did. Or you can pause your screen and study it. Okay, so let's work on one more together. Let's do page 485, number 55. This one looks a little different because the numerator is a little different. We've got x squared plus x, or 1 over x squared plus x. And I'm going to ask you to decompose it into two partial fractions that when you add them together, 1 over x squared plus x. So the first thing we're going to do is factor the denominator. So that would factor into x times x plus 1. So you want to factor into all of its linear factors. And then we're going to write those linear factors as the denominator of new fractions. So the x would be on the denominator of the first one. I do not know its numerator yet, so I'm going to call it a, and the variable a. And then the second one, let's see, changing my colors here. The second one would be b over x plus 1. Now, I want to add those together with a common denominator, but I want to use my common denominator as, keep my common denominator as fractions. So my common denominator would be, of course, x times x plus 1, but my numerator would be a times whatever is missing, and what's missing from the a term over here is x plus 1, so it would be a times x plus 1. Then plus b times whatever's missing from the b term, which would be the x. So now I just want to work with my numerator, and I will say 1 equals a, and I'm going to go ahead and distribute it, ax plus a plus bx. So now I'm going to collect like terms, and I'm going to get 1 equals ax plus bx plus the constant a. Now, when I rewrite this as a system with the coefficients of x and the constant, which or x to the 0, which is the constant, I look on my left side and I see I don't have an x term. I have a constant term, which is 1, but I don't have an x term. So what do? Well, I put a placeholder there, and I call it 0x, because isn't 0x plus 1 equal to 1, right? So now I can write my system. So I'm going to rewrite it here as the coefficients of x, which are a. Oh, I didn't factor. It's really, you can see it though. A plus b times x plus a here. Let's see. So anyway, my system is now going to be a plus b equals 0, because that's my coefficient of x on my left side, and a is my constant. It's the only constant I have, and that is equal to the constant 1. And then I can solve this linear system, which is super simple, because I can just use a substitution, because, or back substitution, because since a is 1, well then what? 1, oh goodness, sorry about that. 1 plus b equals 0, so b would equal negative 1. So now I have my numerators for my decomposed fraction, or my partial fractions. So the numerator that goes over x is a, and a is 1. And the numerator that goes over the x plus 1 is negative 1. So I could write this as minus 1, or I could say plus a negative 1. So 1 over x squared plus x decomposes into the partial fractions of 1 over x minus 1 over x plus 1. And that would be my answer. Take a second to study this, and then I want you to pause the video and work problem number 485, number 60 on your own, and then come back and see if you've done what I've done. And that's page 485, number 60. Okay, so here's the work worked out. And you can see that you can have fractional numerators. And again, this could be 5 halves over x plus 3 plus negative 3 halves over x plus 1. Or you can write it the way that I've written it. Also doesn't matter if you have your terms switched. So you could have had a over x plus 1 plus b over x plus 3. Regardless, when your denominator is x plus 3, whatever numerator letter you give it, it will work out to be 5 halves. And your x plus 1 denominator is going to have a numerator of negative 3 halves. So it doesn't really matter if you did it in the order that I did it, you should still get the same answer, as 5 halves is over x plus 3 and negative 3 halves is over x plus 1. Now the next step we're going to do is we're going to check our work. And the way that we do that is we just combine these two fractions into one fraction and see if we get the number that we started with. So I need to write them with a common denominator, and my common denominator is going to be x plus 3 times x plus 1. Now my green numerator is missing the x plus 1 term, so I'm going to multiply 5 halves times x plus 1, and my blue term is missing the x plus 3. So I'm going to multiply, and I'm going to say plus right here, negative 3 halves times x plus 3. And I'm going to just go to pink here. So what I'm going to do is simplify the numerator and multiply out the denominator. So I get 5/2 x plus 5/2 plus negative 3/2 x minus 9/2, and then my denominator is going to be, when I multiply that out, I forgot my parentheses, is x squared plus 4x plus 3. Okay, when I FOIL that. And now if I add all my like terms up here on the numerator, then I get 5/2 minus 3/2 is 2/2 x, and then 5/2 minus 9/2 is negative 4/2, and then over x squared plus 4x plus 3, and you can see that that does simplify into 1x minus 2 over that denominator, which is what we started with over here. So I did decompose my fraction correctly. And hopefully you did too. Now we are going to do one more example. Sigh. No, really just one more, and then you will have enough information that you can start practicing this completely on your own. We are going to decompose a fraction with repeated linear fractions. So we're going to do example 7 from page 481, but I'd like you to follow along what I do up here, and then I think you'll have enough information to just work on this on your own. So I've written up the problem on here that we have on page 481. And if you look at it, you will see that we now have on our numerator 3 terms. So guess how many lines we're going to have in our system of equations? Yes, that's right. We're going to have 3 lines. We're going to have an x squared line, we're going to a row, we're going to have an x row, and we're going to have a constant row, or x to the 0 row. But we're going to do this the same way we did before. We're going to first factor our denominator. So I'm going to take out my x, because there's an x in every term, and I'm left with x squared plus 2x plus 1. And if y'all don't mind, I'm going to use the same color. Just going to make this easier for me to go faster to just use one color. So anyway, this x squared plus 2x plus 1 can be factored again, and that factors into x plus 1 times x plus 1. Or you can think of it as x times x plus 1 squared. So in other words, I have a repeated linear factor in the denominator. I have an x plus 1, and I have another x plus 1 here, or an x plus 1 squared. And when I do that, I need to have one constant numerator for each power of the repeated fraction. So I'm going to have a constant numerator for my x, so that will just be a over x. But I can't have a b over x plus 1 squared. Or I can't have a b over x plus 1 and a c over x plus 1. I need to have every power represented in a repeated linear fraction. So I'm going to have a b over x plus 1, and I'm going to have a part c over x plus 1 squared. Every power of a repeated linear factor has to be represented. And now I'm just going to follow the steps that I did before. I'm going to find my least common denominator. I'm going to add my numerators accordingly. So I'm going to rewrite my numerator as 5x squared plus 20x plus 6, and it's going to be equivalent to a times something plus b times something plus c times something. So for my a term, what am I missing? Well, I have an x, but I'm missing 2 of the x plus 1s. So I'm going to distribute a to x plus 1 squared, because I have to have both of them. And I'm going to write that as x plus 1 squared multiplied out. So x squared plus 2x plus 1. That is equivalent to x plus 1 squared. My b term, I'm missing an x and 1 of the x plus 1s. So I'm going to multiply b times x plus 1. And I'll distribute that in a minute. And then my c term, I've got the x plus 1 squared, but I'm missing the x, so I'm just going to write, cx right here. So I'm going to go ahead and distribute, and I'm going to get ax squared plus 2ax plus a plus bx squared plus bx plus cx. And now I'm going to collect like terms. So I'll have an ax squared plus bx squared, and then I'm going to have a plus 2ax plus bx, and then I'm going to have a cx, 2ax plus bx plus cx, sorry, and then plus a. So I've collected all my like terms together, and now I'm going to factor them. And I'll write this up again over here, 5x squared plus 20x plus 6 equals a plus b times my x squared plus 2a plus b plus c all times x, and then plus a is my only constant term. So now I can write my system of linear, or actually it's not going to be linear equations. It's going to be my, well, it is going to be my system of linear equations, or it's going to be my system, yes, of linear equations, because I'm only using the coefficients. So my coefficient of x squared is a plus b, I'm going to skip my c, equals 5, because the coefficient of x squared is 5. My coefficient in my right side of x is 2a plus b plus c, so I'm going to write that, 2a plus b plus c equals the coefficient on the left side of x is 20. And then my only constant is a, and my only constant on the left side is 6. So now I have a system of equations that I can solve. I can solve it quite easily because I can just use back substitution because I already know what a is. So because I know what a is, I'm going to write it up here at the top. So I'm going to put my 6, because a is 6, over x, plus, now let's figure out what b is. So a plus b, so 6 plus b equals 5. And when I solve for b, I end up being b equals -1. So I'm going to come up here and I'm going to put a -1 over x plus 1. And then I'm going to solve for c. So 2 times a, so 2 times 6, plus b, which is -1, plus c equals 20. So when I multiply 2 times 6, I get 12, and I subtract 1, I get 11. And when I subtract 11 from both sides, I get c equals 9. So I've got 9 over x plus 1 squared. Okay, and that's my answer, but before I'm done, I should check it to make sure it works. So I'm going to rewrite this, these 3 linear equations, the sum of 3 linear equations, as I'm going to simplify them, find a like or common denominator, and see if I end up getting this equation that I started with here, or this expression that I started here with on the left. So to do that, I'm going to clear my screen so I have room to check it. I know my denominator is going to be x to the third plus 2x squared plus x, so I'm not going to really worry about that right now. I'm just going to work on checking my numerator and see if I can get the same numerator that I had before. Having said that, I am still going to write out my denominator one more time. Okay, so I'm going to write my x to the third plus 2x squared plus x here on the denominator, and then I'm going to combine my 3 numerators. So I'm looking at my 6 over x, and it's missing x plus 1 squared. So I'm going to have to multiply by 6 times x plus 1 squared, which is the same thing as saying x squared plus 2x plus 1. Okay, and then my -1 is missing an x plus 1 and an x. So it's going to be -1 x times x plus 1, just like it did when it was my b. And then here, 9, it's got the x plus squared. It's over x plus 1 squared, so I'm just missing the x. So here's my new numerator. Now again, I'm just going to be working with my numerator here. So I've got 6x squared plus 12x plus 6 minus x squared minus x plus x. Alright, so now I'm going to collect like terms. So 6x squared minus x squared gives me a 5x squared. Okay. And then my 12x minus x is 11x, plus 9x gives me 20x, and then plus 6, because that's by itself. Alright, so that my numerator, it matches my other numerator, and I know that my denominator is x to the third plus 2x squared plus x. So I am right. I decomposed this fraction correctly. Okay, and oh, I erased my p for partial. That's weird. I don't know how they did that. Anyway, this is how you decompose fractions partially. Now, we're not going to do the example on page 482. You can look at it. You can study it if you'd like. Or example 8 or 9. You can study those if you'd like, but you have enough information now to finish your homework for the weekend, and I will collect this on Tuesday. I hope y'all have a great weekend. Have fun in the snow.